So hello everyone, so today we are going to answer this question, why Python is a slow programming language. So let's see what is the first reason. So the first reason is dynamic type binding. We already saw in the previous videos what is the meaning of dynamic type binding. It is one of the features of a Python programming language. It gives you the ability to declare a variable without worrying about its data type. But it has some consequences as well, because the interpreter has to look at that memory location every time you are referring that variable which holds that particular memory content in it. So that is one of the drawback of this dynamic type binding. Interpreter takes a time to look at that memory address every time it refers. And the second thing is interpreted and not compiled. So we already know Python is an interpreted programming language and not a compiled. The meaning of that is interpreted takes single line and perform all the operations and convert that particular line into a bytecode. So it is a time consuming, but in the compiler all the code in a single go converted into a machine code. So that's why interpreter is as slow as compared to compiler. So these are the two primary reasons, but the big and infamous reason of a Python is called GIL, Global Interpreter Law. So what does it mean? So an interpreter does not manage thread on itself. It gives instruction to OS and OS creates and manages the thread. So we saw in the previous videos what is the meaning of parallelism and thread. So to create a thread and to manage that thread, we need OS's help. So let's say there is one function, okay, and thread 1 and thread 2 are calling that function, okay, and that function takes 2 seconds to execute. So by the definition and the concept of multithreading, we can say that thread 1 plus thread 2 takes 2 seconds to execute because they are running in the parallel. But what happened in the Python is that thread 1 plus thread 2 takes 4 seconds to run because they are not running in parallel, they are running in serial manner. But this is a story before Python 3.2. But wait a second, where is GIL in it? So GIL is the one who locks the thread 1 to the memory location, and once it is done, then it removes that lock and then locks the thread 2 to that memory location. So that is the meaning of GIL and that is the use of GIL. So by looking at this image, you can say that Python's memory manager is not a thread safe. So Python uses GIL to check state of thread. So Python uses GIL to check the state of the thread. But how often GIL checks the state of the thread? So we have one parameter called tick. The tick is a bytecode instruction, and when 100 byte code instructions are completed, GIL checks whether the thread are running or it is in the waiting state. Okay, so this is the GIL's working before Python 3.2. So every 100 ticks, GIL checks the status of the thread. Let's say we have 3 threads, T1, T2 and T3. So T1 started its execution and it is waiting for IO instructions. Okay, so after 100 ticks, GIL checks, okay, T1 right now is in waiting state now. Let's start T2. T2 started. Also T2 executed some operations and T2 is also waiting for some operations to perform. Then after 100 ticks, T3 started and T3 executed. Then after 100 ticks, the GIL got to know that T3 is executed and now I need to hand over the GIL to T1 or T2. That is where the battle of acquiring GIL started. So when T3 started its execution, both T1 and T2 are in the waiting state and they are starving for GIL and CPU. So these particular two problems, the battle to acquire GIL and threads are waiting too long, is called signaling and communication overhead. And this type of multithreading is called coordinated multithreading. But this is a story before Python 3.2. Now Python uses fixed time limit approach from Python 3.2 onwards. Here each thread gets fixed amount of time, 5 milliseconds. So by doing that, every single thread now gets same execution time, same waiting time. So let's see the same example. T1, T2, T3 thread. T1 started, after 5 milliseconds T2 started. Then after 5 milliseconds T3 started. Then again T1 gets T2, T3. So by doing that, waiting and execution time for all the threads are become same. So we reduce the first problem, there is no battle of a GIL. We reduce second problem also, there is no battle or no starvation and overload is reduced. But by solving this particular problem, we create or we generate another problem which is called priority inversion. Suppose one thread is about input-output operations and the second thread is about CPU. So here CPU bound threads are getting more priority than IO bounds. But in the real scenario, IO bound should take higher priority than a CPU bound. So that is the problem right now we have in a Python. In this particular multi-threading, or we can say GIL, it is still a research part. So we can do research and we can solve this particular problem by doing that research.